Okay, greetings everyone. My name is Sanga. I am a student at Rhodes University. So today I'll be sharing with you the topic on distinctive mineral assemblages that are present in the carbonate contaminated Flatreef in the Northern Limb in the Bushveld Complex in South Africa. So I really hope you enjoy my talk. So just briefly, the Flatreef is one of the main mineralized horizons that is present in the northern limb, and it is thought to be a correlative equivalent of the critical zone that is present in the eastern and western limb of the Bushveld Complex. So this horizon in the northern limb is placed in direct contact with the Transvaal supergroup sediments, and as such, it shows significant evidence for floor-rock magma interaction. So this interaction has led to the formation of hybrid lithologies, ultramafic lithologies that form the footwall assimilation zone. And the footwall assimilation zone is almost always associated with sedimentary xerites. So for this study, we are mainly focusing on the dolomite influenced footwall assimilation zone. So this is one of the sampled drill cores in the Flatreef, and we sampled from the UG2 correlative downwards into the footwall assimilation zone. And the feldspathic pyroxenite would, in this case, represent the most uncontaminated lithology, whereas the footwall assimilation zone in purple here represents the most contaminated or dolomite contaminated lithologies. So within this footwall assimilation zone, we have identified two main types of assemblages. So the first type of assemblages contains olivine that has a very high phosphorite content that ranges between 84 to 86. There's also intercumulus spinels that has a very high calcium chemical component that goes all the way to 35 mole%. There's also this abundance of chromium spinel that is aluminum rich, and it has a very high magnesium number. And the second assemblage contains olivine that has a relatively low phosphorite content and some intercumulus clinopyroxene that has a relatively low calcium chemical component. In some samples, there's plagioclase, and spinels in this assemblage is only present as chartercrests, and they have very low magnesium numbers as compared to the first assemblage. And in most samples, or in most assemblages, there are these partially resolved relict grains of orthopyroxene, and in most cases, there's also this reverse zone plagioclase chartercrest as well. So in order to try and understand how the dolomite influenced those lithologies, we performed a petrological model. Basically, we did an assimilation fractional crystallization model using the PLA software, which is similar to melt. And then we assimilated a dolomite into the critical zone parental melt. So what we have here is a typically uncontaminated pyroxenite, which is dominated by orthopyroxene, and there's some clinopyroxene here and there, and then there's some plagioclase, and there's little to no spinel in some cases. So the phase equilibrium assimilations show that the olivines that have very high phosphorite content were derived by assimilation of by dolomite assimilation by a relatively primitive melt, and this melt is therefore at high temperatures to be able to liberate large quantities of calcium, some magnesium, and some fluids, including carbon dioxide and water. And these components basically enhance the stability of phosphorite-rich olivine, some clinopyroxene, and some spinel. And like we have here, the model shows that we would have phosphorite content with olivine with a phosphorite content of 86. So this represents like this type of lithology, which I call a wellite, but it's like a hybrid lithology, whereby we have this abundance of clinopyroxene, which is a fasciitic clinopyroxene, which has a very high aluminum component, and some olivine and some interstitial spinel. So the second assemblage is shown to be derived from assimilation by a relatively differentiated melt, right? So what I did was to perform crystallization of an uncontaminated melt and allow it to crystallize up until the astatite component in that in the orthopyroxene was similar to my relict orthopyroxene component, which we have 78 here, and that's 9. And then I halted the crystallization and then activated dolomite assimilation. And instantly we had the removal of orthopyroxene from the liquidus. And then we had olivine with this olivine component, which phosphorus component of 78. And then we have this abundance of clinopyroxene and some plagioclase and almost no spinel because spinel is present as characteristic. So basically what this means is the relict orthopyroxene that are present in my samples basically represent phase disequilibrium with a melt that would basically be becoming progressively silica poor as it mixes with a calcium-rich melt from the dolomite. This is also shown by the reverse sonation in plagioclase, whereby it's becoming ignotite rich from the core to the rim in some samples. So basically this means that the melt is becoming calcium rich, basically, or there's like an addition of a water component in the melt. So here I showed a typical formula of what would happen if we'd have like a dolomite with assimilated dolomite, and then we'd have orthopyroxene in the liquidus. So what we'd have is the formation of olivine and some clinopyroxene and liberation of carbon dioxide. So basically, what this means is that assimilation of dolomite basically changes the liquid line of descent as it progressively accumulates calcium right in the melt. So basically what would happen is if we crystallize orthopyroxene and then we add a calcium component or carbon dioxide and water, we would enhance the stability field of phosphoride and that of dioxide in expense of astatite. So this is also very important in terms of understanding the carbon dioxide and how it would influence the redox conditions, because it would also help us understand how spinels basically stabilize, because we know that spinels are influenced by redox conditions. So that's all I have to share with you guys today. I really hope you enjoyed it.
Thank you very much for presenting.